Okay, thank you very much and welcome back again for this afternoon session. Now, in this afternoon session, we are going to talk about the factor analysis and principal component analysis, which are more related and similar to each other, but in somehow there's some difference between the two, They are more related, more similar, but there's also a difference between the two. So we'll see that what factor analysis is main and principal component analysis, and then we'll demonstrate this factor and principal component analysis by using some data set for the interest of demonstration. Okay, so what are these? Factor analysis and principal component analysis let's see the similarity and the difference between the two, and the way of statistical procedure for principal component analysis and that of factor analysis. So principal component is essentially a method of data reduction which aims to produce a small number of derived variables that can be used in place of the larger number of original measurements, to simplify subsequent analysis of our data. So as you know, like for example, Wales quantile is more of 4 Wales quantile or 3 Wales quantile will be calculated based on the principal components that will be formed. In EDHS report that there are the Wales quantile is recorded as first Wales quantile, second, third, and fourth, maybe until the fifth, So how these Wales quantiles are formed? These types of Wales quantiles, either having 4 or 3 or 5 categories, are formed based on large sets of variables that have been used for collection of the data. And those large sets of data or variables are reduced into a small number of groups by using data reduction technique. So principal component analysis in a very short way it is a data reduction method, So the principal component variables, that are the original variables which are used to collect the data, y1 up to yk, are defined to be linear combinations of the original variables, The original variables x1 up to xq are used to collect the data, and there will be forming a linear combination to form a small set of groups or components which are said to be y1, y2, or up to yk, So the number of principal components that are labeled here as y1 up to yk will be defined or formed with a linear combination of the original measurement variables. So the original measurement variables will be combined in a linear way, and then they will form some numbers of components or principal components or groups. So principal component analysis is a data reduction technique. So the components are the formed components, like for example, first Wales quantile, the second quantile, the third Wales quantile. In the case of Wales quantile, these formed components, the formed components that are just formed by using the original measurements, are unrelated or uncorrelated with each other, and account for maximal proportion of the variation in the original data set. So the variables which will be combined into the one group will be similar with themselves, but the groups that are formed or the components that are formed are uncorrelated. They should be different from each other, So there should be a maximum variation between the groups that we are going to form. So group 1, that means, for example, Wales quantile 1 will be different from Wales quantile 2. Wales quantile 2 from 3 and from 4. So the formed components or groups are uncorrelated, and they should account for the maximum proportion of the variation in the data. Since there is a maximum variation in the data, in the original measurement data, there is a variation. But there is also similarity between with some groups of measurements, So similar measurements or variables will be taken into one group, and another group of measurements or variables which could have another pattern will be formed into another group, and other groups of original measurements having again another pattern will be formed in another group. But the formed groups finally will be different from each other, you know. So the first component, which is y1, that is Wales quantile 1, you can say it, for the accounts for the maximum amount of variance among all the possible linear combinations of the original measurements. And the second component, labeled as y2, should also account for the maximum variance subject to being uncorrelated with the first component. You see, the first component should be uncorrelated or should be different from the second component, and the formed components should account the maximum amount of variance in the original measurement. That is the idea under or behind this principal component analysis. So this principal component analysis, or PCA, is an approach to data reduction to create one or more index variables. That means index variables means group variables. Finally, after the huge data, the blown up data has been reduced by the by the PCA approach, data reduction approach, finally we will have index variables. That means components or groups from a large set of original measurement variables, you know. So it does this by using a linear combination of the set of variables. So a set of variables will be combined into one group which are more similar to each other, and other groups of variables will be grouped in another component which are similar with each other within that group, but the groups formed will be different from each other. So the created index variables are called finally components. The group variables that we are going to form are said to be the components, you know. So the whole point of the principal component analysis is to figure out how to do this in an optimal way. How do we do this principal component analysis? That is the point, you know. So the optimal number of components, how do we determine the number of components? The number of groups that we are going to make, how we are going to determine the number of groups or the number of components, whether it is 3 or 4, based on the original measurement data, how many groups should be there, how it would be determined, you know. That is the idea behind the principal component analysis. So the optimal choice of measured variables for each component and the optimal weights or contribution of each variable to that group, you know. So the picture on the next slide shows that the PCA is doing to combine 4 measured variables into a single component, you know. 4 originally measured variables will be combined into one group. And you can see from the direction of the arrow that Y variables contribute to the component. Maybe let's have a look at on the graph first, you know. Here is a graph. So here is a component which is going to be formed, you know. And here Y1 out to Y4 are the original measurement variables. They are combined into one to form this component variable or to this group. So each of these individual variables have their own contribution. That is said to be the weight. The weight of the first variable to the component, the weight of the second variable, the third, and the fourth. This W1, W2 up to W4 represents the weight or the contribution of each original measurements to the component that is going to be formed. So mathematically, maybe with a simple equation, we can put in the form of this equation. The component C is equal to the contribution, that is the weight of the first variable, plus the weight of the second up to the weight of the fourth variable. So this is a way. You know, these 4 variables are merged into one to just form a single category. So they are reduced into one variable, you know. So that is a data reduction technique has been said for PCA. What about the factor analysis? There are similarities and there are differences, as I've said before, Factor analysis is a technique for investigating whether a latent variable or variables underlie a set of item responses. In the case of factor analysis, what we are going to do is, for example, in the case of principal component analysis, we are going to just merge a number of original measurements to form groups of components, simply. But in the case of factor analysis, there is a real variable, but that variable cannot be measured directly. As I have said repeatedly, maybe if you have seen my structure equation modeling videos in the YouTube channel. So these latent variables are those variables which cannot be measured directly. Like, for example, take depression, anxiety, PTSD, health-related quality of life, psychosis. A number of medical variables are there. We are not going to form these variables, The variables are there in the life of individuals. In daily activities of the individuals, the variables are there. We are not going to form. But we cannot directly measure these types of variables. You cannot directly measure the depression. How do you measure? How do you measure anxiety or PTSD or psychosis or quality of life or satisfaction with a health-related service activity, health service of a certain hospital or any health facility? How do you measure these variables? These variables cannot be measured directly, So factor analysis is concerned with the investigation of whether these types of latent variables, these latent variables are those variables which cannot be measured directly. Rather, we measure these latent variables indirectly with other items of questions. Like, for example, how do we measure knowledge of an individual on HIV/AIDS? Can we measure it directly? No way to measure it directly, Rather, you could use either 5 or 10 items of questions related with HIV, with its prevention and risk factor, whatever. So that these latent variables are those variables which cannot be measured directly. Therefore, factor analysis is concerned with to investigate whether a latent variable is underlying with a set of items of response variables. That means whether there are appropriate items of questions which are used to measure such types of latent variables. You see, by doing so, finally, like for example, if you see the DSM-5 criteria for the clinical diagnosis of mental health disorders, there are a list of items of questions. And by using those items of questions, finally, the physician or the health professionals would say that the patient is positive, have anxiety or without anxiety, have depression or without no depression. Finally, it will be also a data reduction technique. But the way how the data is reduced is in the way such that the items of questions are used to measure an observable variable, the variable which cannot be directly measured, So that is the purpose of or the objective of factor analysis, in order to investigate whether a set of item responses or questions are appropriate enough to measure a latent variable. That is it. In the principal component analysis, it is not going to test whether those items of questions are appropriate enough to measure that component variable finally. That is not the intention of principal component analysis. Rather, simply what does principal component analysis do is that it only combines those questions of items which are more correlated with each other, with one group, and other items of variables which are correlated with each other, having another pattern in another group, and those combination of variables should account for a maximum variation in the original data measurement, That is the intention of PCA and factor analysis. So in factor analysis, if there are multiple latent variables underlying the item responses, this factor analysis is also used to evaluate the relationship among the latent variables. Okay, now I should draw some diagrammatic representation here in order to explain this bullet, Let's have a look at over here, for example. Now let me say I do have a depression. Depression is a latent variable, which would be measured by item number question 1, number question 2, and number question 3. Let's say that there are 3 items of questions to measure depression. And I do have another latent variable, anxiety, which is again going to be measured by using other items of questions like question number 4, question number 5, question number 6, and question number 7. There are 4 items of questions to measure this anxiety, you know. Okay, what factor analysis is going to do is, you know, factor analysis will investigate whether this latent variable is really have an underlying items of questions, whether these items of questions are appropriate enough to measure this latent variable. And again, similar with the appropriateness of these questions to measure anxiety, 1. And the second thing is, if there is a relation or a correlation between depression and anxiety, it will also control or investigate the correlation between these two latent variables, in which principal component analysis cannot do this, you know. Therefore, even if both principal component analysis and factor analysis are a data reduction techniques, but in somehow they are very different, in which factor analysis can assess whether a certain items of questions are appropriate enough to measure a latent variable, and also it can measure the correlation between these two latent variables. Even we can have another third latent variable like PTSD, you know, PTSD, measuring other items of questions like number question 8, number question 9, number question 10. And if we suspect that there is a correlation between PTSD and anxiety, we can investigate the correlation between these two. And PTSD with depression, again, it can be measured or investigated, you know. That is the idea of factor analysis. So it is very different. Even if both of them are data reduction techniques, factor analysis and the way in which factor analysis and the way in which principal component analysis do the data reduction is very different. So this is the idea under factor analysis. So this is concerned with whether the covariance or the correlation, that means between a set of observed variables, can be explained in terms of a smaller number of unobservable constructs known as the latent variable. That I have said. You see, if you have 10 items of questions to measure depression, so there should be a correlation between the 10 items of questions with the latent variable depression. So that the intention of factor analysis is concerned with whether there is a correlation between the set of observed variables, that means the items of questions, with that of the smaller number of unobservable constructs, that is the latent variable, the depression, maybe, or the anxiety. Okay, so the correlation between each pair of measured or manifest variables, that means the items of questions, arises because of their mutual association with the common factors. You see, in addition to the correlation of these items of questions with the latent variable, there should be also a correlation between the items of questions with themselves. They are correlated with each other, the items of questions with each other, because they do have a mutual association with what? The common factor, that is the depression. Maybe if we are talking about an example of depression. So the items of questions which are used to measure depression are correlated with each other because they do have a mutual association with what? With the latent variable depression. So it is a model of the measurement of a latent variable in factor analysis. So factor analysis is simply a measurement model for a latent variable. In structural equation modeling, there are two models, measurement model and structural model. And please refer to the YouTube channel in order to understand what does structural model mean and measurement model mean, you know. That is why I am really interested to show you what does this structural modeling mean, because this is related with factor analysis here. And there's also a confirmatory factor analysis there in a structural ecology modeling, which is very related with factor analysis. And factor analysis is one component of structural ecology modeling by itself, in addition to the confirmatory factor analysis. So that this latent variable cannot be measured directly, as I have said before, like anxiety, food quality, quality of life, satisfaction, extra variables cannot be measured directly. So instead, it is measured through the relationships it causes in a set of y variables. That means items of questions. So that is the factor analysis concept, you know. Factor analysis is a multivariate statistical technique that can summarize the information from a large number of variables into a small number of variables or factors. Why this is multivariate? This is a multivariate statistical test, you know. Multivariate refers to having more than one outcome variable at a time in a regression model, or maybe in any statistical test, having more than one outcome variable at a time. So how factor analysis can be a multivariate, or how factor analysis could have more than one outcome variable at a time? How it could be? Let me show you again the previous graph that I was showing you, you know. Depression, one outcome variable, that is dependent variable measured by items of questions from 1 up to 2. So these are items of questions, and depression is an outcome variable. Okay, now anxiety is again measured with the 4th question, the 5th question, and the 6th question. These are items of questions used to measure the anxiety. Anxiety is an outcome variable. Okay, here I do have, let me have a PTSD, an outcome variable measured with items of questions 7, 8, and 9. So PTSD is another outcome variable. So we are going to correlate or measure the correlation between these three outcome variables. So at a time we are investigating more than one outcome variable: depression, anxiety, PTSD. So factor analysis is a multivariate statistical test that is going to reduce the number of large sets of variables, you know. So the large sets of the variables are the items of questions that have been used to measure these three latent variables. There are at least 9 questions, you know, 9 items of questions to measure. And if these 9 items of questions have been asked for 400 sample size or individuals, then that will be huge. So by just this technique, it can reduce the large sets of variables to measure, and plus it is a multivariate technique. It can just investigate the relationship of more than one outcome variable at a time. So that is the idea which is written here in this bullet. So it is often referred to as, it is also named as exploratory factor analysis. This factor analysis is said to be exploratory factor analysis. Why? What do we explore? We explore the relationship or the factor loading of items of questions which are used to measure a latent variable. We are exploring the variables or items of questions which could be appropriate enough to measure the unobserved outcome variable. Because of this, it has been said or called as exploratory factor analysis, you know. Because the technique explores data patterns to identify the factors. The word factors refers to hereafter, please, it is latent variables. Factors, the latent variables. Item responses are items of questions used to measure the factors, you know. So the relationship or the pattern between the items of responses with that of the factors, it will be investigated or explored, you know. That is why it is named as exploratory factor analysis. We are exploring the pattern or the relation of items of questions or items of responses with that of the factors or the latent variables. That is why it is named as exploratory factor analysis. So by identifying the latent variable that is not easily identifiable or directly non-measurable variable, the relationship and combining variables, that is the items of the questions, into a smaller number of factors. Exploratory factor analysis simplifies our understanding of the data. it reduces the huge amount of data collected by the original variables into a smaller number of factors or latent variables. Like for example, the DAS-21 scale, depression, anxiety, and stress scale, have 21 items of questions. But these 21 items of questions are used to measure depression, anxiety, and stress. 7 items for depression, 7 items for anxiety, and 7 items for stress. So those 21 items of questions will be reduced into 3 latent variables finally, into depression, anxiety, and stress. That is simplification of our understanding of the data, you know. And finally, confirmatory factor analysis will follow next to this exploratory factor analysis. The confirmatory factor analysis is an analytic technique used to study the relationship between multiple indicators. Multiple indicators means multiple item questions or items of responses. And a latent variable. A latent variable, the variable that cannot be measured directly. So what does this confirmatory factor analysis do? It measures the factor loadings or the correlation of each items of questions with the latent variable by calculating its confidence interval or the p-value, whatever. So we can say that we can test or confirm either the items of questions are statistically significantly appropriate to measure that latent variable or not. So the way how do we confirm that items of questions are statistically appropriate enough to measure the latent variable will be confirmed by doing a confirmatory factor analysis, because beyond the factor analysis, it will calculate the p-value, the standard error, the confidence interval in order to judge statistically whether they are significant or not. But in the exploratory factor analysis, what does it do is only it calculates the correlation coefficient. In confirmatory factor analysis, we can calculate the confidence interval, the standard error, the p-value, blah things. And then finally, we can just prove items of questions and delete from the list if they are not statistically appropriate to measure the latent variable. That is the confirmatory factor analysis. So I think by now you have understood what does principal component analysis and the intention of factor analysis, you know. So confirmatory factor analysis is the most widely used technique for specifying latent variables in the measurement model within the structural equation modeling framework. So confirmatory factor analysis is simply the measurement model component of the structural equation modeling. Two models are there, as I have said before, structural model and measurement model. So the measurement model of this structural equation modeling is said to be the confirmatory factor analysis, you know. So the measurement model, that is the confirmatory factor analysis, for a simple one-factor model looks like the diagram in the next slide. That means if we do have only one latent variable, that is one factor. You see, the measurement model for a simple one-factor model, if we do have only depression being measured under the study, that is one latent variable. That is one factor means one latent variable. So it's the diagram will look like in the next slide. Let me show you. Here it is, you know. Now, here is a factor. Like in the principal component analysis, you could think as a component, you know. And these are the items of questions or indicator variables. And they do have their own beta coefficient, B1, B2, B3, and B4. You see, what is different from the beta coefficient is also an additional thing here is the error term are associated with each of the items of the questions. Error term for the first question, the second question, error term for the third, error term associated with the fourth question. You see, factor analysis measures the errors associated with each items of questions while they are trying to measure the latent variable, you know. Each of the items of questions have a contribution to measure the latent variable, but none of them can perfectly measure the latent variable. So that if they cannot measure perfectly the latent variable, always there will be error associated with each items of questions. So the error associated with each of the items of questions will be measured in factor analysis, which was not the case in principal component analysis, you know. Only in principal component analysis, what were included in the diagram is the component, the items of questions, and their contribution or the weight only. There was no error term associated with the items of questions, you know. So why? So that which question will be more appropriate enough to measure this latent variable? The variable having a higher error is the more inappropriate to measure that latent variable. The item of question or the variable refers to the item of question. Having a smaller error is the more appropriate item of question to measure this latent variable, you know. That is the factor analysis and confirmatory factor analysis is going to do. So in mathematical formula, we can just have such equation. Y1, this item of question, Y1 is equal to beta 1, this factor, the latent variable, plus the error term. And for all the others, again, similar. So underlying factors are often variables that are difficult to measure. These factors or latent variables, like intelligence quotient, depression, extraversion, anxiety, blah, blah things, you know. For measuring this, we often try to write multiple questions that at least partially reflect such factors, partially measure these latent variables. The basic idea is illustrated on the next slide again, you know. Here it is. There are items of questions from 1 up to 9 items of questions. Out of these 9 items of questions or variables in the data, some of them are used to measure the numeric IQ level, some of them are used to measure the spatial IQ level, and some of others are used to measure the verbal IQ level, you know. So 1 up to 3, questions from 1 up to 3 are used to measure the numeric IQ, 4 up to 6 they are used to measure the spatial IQ, and the remaining 3, 7 up to 9 are used to measure the verbal IQ. And we expect there could be a correlation between numeric IQ with spatial IQ with verbal IQ, and again numeric IQ with verbal IQ. There will be a correlation between these latent variables, you know, in factor analysis. This is what we are going to do in factor analysis. And actually, please, I'm urging you to just refer to the YouTube channel about the confirmatory factor analysis, especially the measurement component YouTube, that video that is already uploaded in the YouTube, you know. You will get some extra explanations and examples there. So the factor analysis in this question, I have said already, questions 1 up to 3 are used to measure numeric IQ, and the rest are already explained, you know. So finally, let's have a correlation matrix in between the questions of items of questions, you know. Question 1 with question 1, since it is correlated with itself, the correlation will be 1, you know. Question 2 with question 1, the correlation coefficient 0.75. Question 2 with question 2, it will be again 1, because it is correlated with itself. So by this, we need to appreciate how these items of questions are correlated with each other. The items of questions which are going to be used to measure a latent variable are correlated with within themselves, you know, because they are associated with some an underlying or unobservable latent variable. They are associated with the underlying non-directly measurable latent variable. So we expect a correlation between each of the items of questions if they are trying to measure the same thing. Otherwise, if they do not have any correlation between them, they cannot measure the same thing, you know. So this is a correlation matrix we will see. Factor analysis takes a large number of variables and reduces or summarizes it to represent them in different smaller factors, that is the latent variables. Those factors are made up of the initial set of items of questions or variables. So factor analysis is a method for investigating whether a number of variables of interest are related to a small number of unobservable factors. Whether these sets of items of variables or questions are related with the latent variables simply. Are they related with the latent variable and with themselves? So this way of relationship is done by grouping the variables based on intercorrelation among the set of variables. Intercorrelation among the set of questions or variables is expected if they are going to measure the same thing, you know. Unless and otherwise there is intercorrelation between the items of questions, they cannot measure the same thing, you know. They cannot measure the same latent variable. So those initial variables are the manifest variables, the original measurement variables, or the items of questions that are used to measure, or said to be the observed variables. I have made a very well explained video on the language of structure equation modeling, which deals more about this issue, you know. So those initial variables are the manifest variables or observed variables, while the factors are the latent variables, which will be extracted in the process of constructing these latent variables, you know. Like depression is a latent variable, but the items of questions used to measure depression are observed variables. That is simply what factor analysis is going to do. So a common usage of factor analysis is in developing scales or questionnaires for measuring constructs. That means for measuring latent variables that are not directly observable in real life. If you refer to the psychiatric book which talks about the DSM-5 criteria, those DSM-5 criteria listed there are approved by the use of this factor analysis, confirmatory factor analysis, you know. So this factor analysis is used to develop a scale of items of questions which are used to measure a certain construct that cannot be measured directly. WHO quality of life questionnaires, the WHO disability assessment schedule questionnaires, all those scales, different scales, you know, the nutritional measurement scales, whatever, all those scales will be proved or disapproved by the use of factor analysis. So the factor analysis technique primarily examines the systematic interdependence among a set of observed variables, among a set of observed questions, items of questions. That means I said that there is interdependency between items of questions if they are going to measure the same thing. And then there should be a correlation. So we need to measure this interdependence of between items of questions or variables by using a correlation. So the correlation matrix should be reported, you know. And those variables that have higher correlation are grouped together. Variables having higher correlations will be in one group. Factor analysis will help the scholars to answer the question that how well do the items go well together, you see? Which items of questions will be in one group to measure one specific disease? And which other items of questions will be in another group to measure other type of disease? Will be determined by using the factor analysis. In case if we are developing or building a new scale. When the new scale is being developed, this will be done by the approach of this factor analysis in such a way, you know. So what is the similarity and the difference between factor analysis and principal component analysis? Both are data reduction techniques. That's the similarity. They allow you to capture the variance in variables in a smaller set. Both of them will just reduce the large set of the variable into a smaller set. In PCA, it is called a component, and in factor analysis, it is called a construct or a factor or a latent variable. Both are usually run in softwares and even using the same procedure in running during the software. And the output also looks like pretty much the same. The steps you take to run them in the software are the same. The extraction method, the interpretation, the rotation, choosing the number of factors or the number of components is similar. But despite all these similarities, there is a fundamental difference between them, as I have said and explained it very well previously, Principal component analysis is simply a linear combination of variables. It does not measure whether each items of questions are correlated with each other or not. Plus, it does not measure whether each items of questions or variables are related with the latent variable, whatever. And it is not going to measure a latent variable. Simply, it is going to measure a new variable simply in PCA. And that new variable simply will be just simple naming, simply naming. Lowest quantile, second quantile, first quartile, fourth quartile. This is just simply naming, instead of saying first quartile, second quartile, you can say the lowest socioeconomic status, the middle, the higher, blah blah things. Alternative names are there for PCA, Just simply labeling and attaching a name for the newly created component. That is the idea of principal component analysis. It does not going to measure an observable variable, But in factor analysis, it is a measurement model of a latent variable. It is going to measure a latent variable. And it will measure the correlation between items of questions with themselves and the correlation between these items of questions with the latent variable. So in factor analysis, we are not going to create a new variable. The variable is there always. Rather, we are going to measure that variable which cannot be measured directly. But in PCA, we are going to create a new variable based on the original measurements, So there is this fundamental difference between the two. The objective of PCA is to reduce the number of variables to a few components, such that each component forms a new variable, as I have said. And the number of retained components explain the maximum amount of variance in the data. So the objective of principal component analysis, while it is trying to form components, is it tries to capture or explain the maximum amount of variance in the data. While in factor analysis, the objective is to measure the correlation of items of questions with themselves and with the latent variable, not the variance. So the objective of factor analysis, on the other hand, is to search or identify the underlying factors or the latent variables that can explain the intercorrelation among the variables. So the intention of factor analysis is in order to investigate the intercorrelation between variables. And the objective of PCA is in order to explain the maximum amount of variance in the data. You see? Therefore, there are two major differences. First, the PCA analysis places emphasis on explaining the variance in the data. Whereas the objective of factor analysis is to explain the correlation among the indicators or the original or the observed measurements. So the emphasis in PCA is to explain the variance in the data, and the objective of factor analysis is to explain the correlation among the observed variables. And the second difference is in principal component analysis, the variances form an index variable, a new variable, like Wells index. We are going to form a new variable or create a new variable. Whereas in factor analysis, on the other hand, the variables or indicators, that means the original items of questions, reflect the presence of an observable construct or a factor. We are going to measure a latent variable. We are not going to create a new variable in factor analysis, We are simply going to reflect or investigate the presence of an observable factor, a latent variable. But in principal component analysis, we are going to create a new variable. with the combination of the original measurements. That is, the component is formed by the original variables x1 up to xp. So the variables are called formative indicators of the component, as the index is, or the group for the component is formed by these variables, you know. So that is a big difference between the two. In factor analysis, in other words, the indicators reflect the presence of an observable or latent construct or latent variable or factor, and hence the variables are called reflective indicators or response items of response, or indicator variables simply, in factor analysis, you know. So that is a big difference between the two. Now, hereafter, how we are going to do this factor or principal component analysis. The following is the list of some basic terms frequently used in the factor analysis and in principal component analysis. The first one is the Kaiser-Meyer-Oakley. That means KMO, measure of sampling adequacy. This KMO test measures whether the sample size that we have is adequate enough or not. So the KMO, measures of sampling adequacy, is a statistics used to examine the appropriateness of a factor analysis based on the sample of the study, the sample size. So the higher the KMO value, that will be the better. If KMO value is between 0.5 and 1, if it is above 0.5, then it indicates that factor analysis is appropriate to do for the data. Whereas if the KMO value is below 0.5, then factor analysis is inappropriate, you know, because the sample size is not enough, not appropriate enough. This means that the sample is not enough for exploratory factor analysis. So we need to check first this one, whether we do have appropriate sample size or not. The second one is the Bartlett's test of sphericity. This Bartlett's test of sphericity is a statistic which is used to examine the hypothesis that the variables are uncorrelated in the population. The items of questions or the indicators are not correlated. That is the null hypothesis. The population correlation matrix is an identity matrix. Each variable correlates perfectly with itself, but not correlated with other items of questions. So that the null hypothesis says that the original indicator variables are not correlated with each other. The alternative is there is a correlation between each indicator variables. So if the p-value is less than 0.05, then there is a correlation between items of questions, so that we reject the null hypothesis. If the p-value is greater than 0.05, that means there is no correlation between the items of questions or between the indicator variables, you know. So that is a very good statistical test. I have already said p-value of 0.05, below that and above that, you know. The other test in software is communality, you know. Communality is the amount of variance a variable shares with all the other variables being considered, you know. So the amount of variance that a specific variable is sharing with other variables. So small values indicate the variable do not fit the well with the data, and should be dropped from the model, you know. If, for example, if it is less than 0.5 and below that, if the communality for a specific variable is below 0.5, then that variable should be removed because it does not share an amount of variance or appropriate amount of variance with other variables. It does not share such amount of variance with other variables. The other is the percentage of the variance. It gives the percentage of the variance that can be attributed to or due to each specific factor relative to the total variance. So the contribution of the percentage of variance for each variable relative to the total variance, you know, that is the percentage variance for each indicator variable. Eigenvalue, which is very important, you know, the eigenvalue represents the total variance explained by each factor. the total variance explained by each item of question separately. So factors having eigenvalue of 1 are selected for further study. If the eigenvalue is below than for any for any indicator variable, that variable will be removed from the model, Another is the script root. The script root is a diagrammatic or graphical display of this eigenvalue. So it will show us the eigenvalue in the form of the graph. Other than that, there's no difference between the two. The script root is just the optimal number of factors will be determined based on the... So now, the number of components in PCA or the number of latent variables, maybe in factor analysis, are determined by based on the eigenvalue. The point at which the eigenvalue dropped or become below 1 will stop there, and the number of components will be determined at that point. We'll see it in the example dataset, Factor loading is simply the correlation between each indicator variable with the latent variable. The correlation between each indicator variable with the latent variable is factor loading. Factor loadings are simple correlations between the variables and the factors, that is, the latent variable. Factor loadings show how well the items represent the underlying factor. The higher the correlation of each items of questions with the factor or with the latent variable, that is the better. But the lower the correlation, the items of questions are inappropriate to measure that latent variable. And then finally, we'll have factor matrix. A factor matrix containing the factor loadings of all variables. Simply the correlation matrix of all combinations of indicator variables on all the factors that have been extracted, So these are the steps that we need to follow in doing factor analysis or principal component analysis. One, we need to identify the problem. The first step, problem identification. The second one is exploratory factor analysis requirements. The assumptions that we have seen before should be fulfilled, adequate sample size, sphericity, whatever. All these things, the requirements should be checked first before doing the analysis. The third step is appropriate factor technique. Appropriate factor techniques should be selected in the procedure of doing it in the software. Plus decision regarding the number of factors or components. How many factors or components should be made. Okay, next is rotation technique. What does rotation mean? We will see that. And then the sixth is the model fit, whether the model fitted well or not. The seventh one is finally running exploratory factor analysis. And then finally interpretation and reporting. And naming of the components, in PCA. So checking the assumptions. A principal component factor analysis requires the variables included must be continuous or at least dichotomous, binary. It should be continuous or it should be yes and no. The variable should have only yes and no response. If we do have categorical type of questions, sorry. Okay. So it should be either continuous or a binary nominal label. So all the indicator variables should be in this form, Do you have television? Yes and no. Do you have radio? Yes and no. It should be in such a way. Or weight, monthly income, whatever. This will be continuous. The sample size must be greater than 50, at least preferably 100. And the ratio of the cases to the variables, that means the ratio of the samples to the variables, the number of items of questions that we have must be at least 5 to 1. That means for one item of questions, there should be 5 individuals or samples, simply. The correlation matrix for the variables must contain at least 2 or more than 2 of having a correlation of 0.3. There should not be an item of question having less than 0.3 correlation. If it does have, it will be removed, So the correlation matrix should at least contain for 2 variables at least 0.3 and more than that correlation coefficient. Variables with measures of sampling adequacy less than 0.5 must be removed. We need to look at the test of Bartlett's test, you know. Okay, the overall measure of sampling adequacy 0.5 and above should be above that. If it is below that, it will be inappropriate. So that finally, the Bartlett's test of sphericity should be statistically significant for factor analysis and principal component analysis to be appropriate, you know. So the first phase of principal component analysis is devoted to verifying that we met these assumptions. If we do not meet these requirements, factor analysis is not appropriate. So that should be taken for no granted, you know. Okay, now interpretive adjectives for the KMO measures of sampling adequacy are given here. And generally, if it is below 0.5, that will be unacceptable, you know. The KMO value should be at least 0.5 and above. If it is beyond 0.9, that will be marvelous, and the others are given there, you know. And the step 2, the second phase of principal component factor analysis focuses on driving a factor model, a pattern of relationship between variables and components that satisfies the following requirements. The derived components explain at least 50% of the variance in each of the variable. So the communality for each variable should be at least 0.5 and above. The share of percentage of the variance in each indicator variable should be at least 50% and above. Okay, none of the variables should not have, or none of the variables have a correlation of 0.4 or less than that. Sometimes it is being taken as 0.3 or higher for more than one component. Do not have complex structure. You see, one variable or indicator variable should be placed only in one component. If it is placed in two or more than two components, that will be complicated. And in order to solve that complication, we will use rotation method. By rotation, that complication will be removed, you know. We'll see what rotation means. So none of the components has only one variable in it, you know. If a component is measured only by one variable, how it could be taken as a component? At least to be a component or a latent variable, it should be measured by at least 2 items of questions and more than that. If you measure a latent variable with a single item of questions, that cannot be taken as a latent variable. That means if you can measure it by a single question, that means you can measure it directly. So none of the components should have a single variable in it, you know. So to meet these requirements, we remove problematic variables. If either of the items of questions do not satisfy these assumptions, that variable will be removed from the analysis. And then we will do the analysis again by removing that specific variable. Okay? If at the conclusion of this process, if we have components that have more than variable loading on them and have components that explain at least 50% of the variance in the included variables and have components that collectively explain more than 60% of the variance in the set of variables, we can substitute the components for the variables in the further analysis. Okay, we'll see it anyhow. Variables that were removed in the analysis should be included individually in further analysis, but just a number of trials will be done. Substitutions of components for individual variables is accomplished by using only the highest loading variable or by combining the variables loading on each component to create a new variable, you know. So note please, have this attention. When evaluating measurement of sampling adequacy, communalities or factor loadings, we ignore the sign of the numeric value. If it is negative, we ignore the negative sign and simply we should focus on the value. The negative sign tells us the direction of the correlation. negative correlation and positive correlation. So we need to ignore the negative and the positive signs, you know. Simply focus on the value or the amount or the magnitude of the score. So now here we do have an example. Research questions and data were just there in a survey which was held among 388 applicants for unemployment benefits. The data was collected in Dole's World Survey. This is the name of the data set. The survey included 16 questions to measure the client satisfaction, you know. 16 questions to measure client satisfaction. And we think these measures measure in a small number of underlying satisfaction factors, but we have no clue about a model. We are not going to measure these items of 16 questions individually, you know. Rather, they may measure 16 items of questions. Some of them may measure some aspect of satisfaction. Other items of questions may measure other component of satisfaction. So we want to just form a component, you know, but we do not have any clue how to form that. So our research question for this analysis is how many factors are measured by these 16 questions. How many factors means how many latent groups or components are measured by these 16 questions. Which questions are more similar to each other? Which questions measure similar factors? And which other questions will measure other factors? Okay, which satisfaction aspects are represented by which factors? You see? Which satisfaction aspects are represented by which factors? So this should be answered by doing this principal component analysis and or factor analysis. Now the steps that we are going to follow in SPSS is just displayed here. So these are the requirements that should be selected in doing the analysis. We'll do it. Finally, the result will be displayed in such a way, you know. Here, what is given here is the component, the number of components listed. From 1, it will be listed until 16. You know, each items of question could be considered as a single component. 16 component could occur there. So the software will consider in such a way that each items of questions will measure a separate or a single component. That is assumption, but that will not be the reality. So until the 16, the number of questions that we have, there will be a number of components with that amount, you know. Okay, to determine the number of components that we will have, we need to look on the eigenvalues, the initial eigenvalues. Okay, component 1, the eigenvalue is 2.43, the total eigenvalue, and the percent of share in the variance for the first component is this much. For the second component, the eigenvalue is 2.34, and the percent share of the variance is 14.6. For the third component, the eigenvalue is now becoming 1.93. For the fourth component, eigenvalue is now 1.58. If we make the component to be 5, the eigenvalue is now below 1. So the component cannot be 5. Rather, we will have 4 components, depending on the cutoff level of this eigenvalue. Eigenvalue of 1 and above will be used to determine the number of components that we will have. So the 16 items of questions are used to measure 4 components. So these items of questions will be grouped in either of the 4 components hereafter, you know, hereafter. That is the idea. So this is the way how we are going to determine the number of components. Like, for example, the Wales index, number of Wales indexes in EDHS are determined in such an approach. So here is what has been already said. There will be 4 components. Again, okay, let's have again the script plot, which is an alternative for the tabular form of the eigenvalue. The eigenvalue is here in the y-axis, and the number of components are given in the x-axis. So when we do have 1 component, eigenvalue is above 2.5. When 2 components are there, it is exactly 2.5. When it is 3, it is in between 2.5 and 2. When it is 4, it is almost above 1.5 but below 2. When we do have 5 components, here, look over here. Now the eigenvalue is below 1, you know. So it cannot be more than 4 components. So we will have only 4 components. So these 16 items of questions will be grouped in either of the 4 groups or components. So we will have 4 components or maybe factors. Now, here is the explanation, I think. You see, so to what extent do our 4 underlying factors or components account for the variance of our 16 input variables? This is answered by the R square in regression analysis, and which is called communalities in this factor analysis. Okay, in factor analysis is communality. So if we predict variable 1 from our 4 components by multiple regression, it will be 0.596. That is a communality for variable 1. Variables having low communalities, that is below 0.4, will be dropped from the factor analysis. So let's have this result, you know. This is a communality table. Each of the items of questions, the 16 items of questions are listed here. And their communality is given here. The percentage. Look, all the items of questions. All of them are 0.4 and above, or 40% and above. So all of them have explained some amount of variation in the factor, you know. So all of the items of the questions are appropriate enough. But if one of the question is below 0.4, then that variable will be, or that question will be dropped from the analysis. And the factor analysis will be reanalyzed, you know. Okay, now the component matrix will tell us one thing, you know. So far, we conclude that our 16 variables are probably measuring 4 underlying constructs or components. But which items measure which factors or which components is not known yet. We determine the number of components. But which variables measure which component is not known yet. So how do we know that? The component matrix shows the Pearson correlations between the items and the components. Now let me show you just the output, you know, the result. Over here. Here is a component matrix. Look over here. Here is a component 1, component 2, component 3, and component 4. Okay, here are the list of the 16 items of questions. See, for example, variable 17, variable 16, variable 13, and variable 2, or 21, I think. Sorry, 2, it is 2. These items of questions are measuring component 1. Therefore, they are used to, or they are grouped in the component 1. Okay, now let's see the last one. Variable 4, variable 14, and variable 12 are grouped for the 4th component. So they are used to measure the 4th component. Okay, now just here around variable 20, variable 6, variable 7, variable, these 3 items of questions are used to measure again for component 2 and for component 3. That is very difficult. These items of variables are grouped for the 2 components. So for this, to solve this, we will do a rotation technique. By rotation technique, for which component these items of questions will be more appropriate, will be selected by the software, by the rotation technique, you know. So they will be grouped only for 1 component hereafter. But in this output, they are trying to measure 2 components. Even look over this variable 3. Variable 3 is trying to measuring the 3 components, component 1, 2, and 3. Again, variable 11 also is trying to measure component 1, component 2, and component 3. So that is very difficult. So this problem will be solved by the use of rotation method. By rotation method, that means each of the items of questions that are belong to more than this 1 component will be tested one by one for each component, And for the one which they are found to be more appropriate will be placed there and then removed from the other component, That is the rotation technique is going to do. So here this slide is talking about this issue. So now the solution for this is by using the rotation method, as I have said. That is the rotation method that we are going to use in SPSS is the Varimax rotation method. The Varimax is abbreviated form of the variable maximization rotation method. So that will be used in order to solve such an overlap of a certain item of question to more than one component. So our rotated component matrix in the next slide answered our question, which variables measure which factors. So now let's have a look at over there, Here it is. See the labeling here, rotated component matrix. Now by this rotated component matrix, all the items of questions are placed only in one of the four components. Look over here. So these items of questions are used to measure component 1. These items of questions are used to measure component 2. These items of questions are used to measure component 3. And the last, these items of questions are used to measure component 4. So that is the way how principal component analysis is being done. Now, the last thing that we are going to do is our last research question. What do our factors represent? You see, what do component 1, what name should be given for that? Component 2, what name should be given for that? Okay, now by reading the meaning of the questions that are used to measure each component, for example, we need to read the ideas included in items of questions from this to measure this component 1. So we need to give a one common name for which these items of questions are trying to measure. So that component 1 will be named according to the meaning of the items of questions that they are trying to measure. And for the second one, for the third, and for the fourth one, in a similar approach, Okay. So like, for example, technically, a factor or a component represents whatever its variable have in common. So our rotated component matrix above shows that our first component is measured by variable 17, variable 16, 13, and 2, and 9. And we need to read the questions or the items of questions there in the variables listed, So note that these variables of all relate to the respondent with regard to clarity of information. They are asking about the clarity of the information, all these questions. So we can name the components that they are trying to measure as, we can give a name clarity of information. For what? For component 1. Rather than saying 1, 2, 3, we need to give appropriate name according to the questions that they are trying to measure, the meaning that is attached with items of questions of that specific component. So according to this, we need to give appropriate naming for the remaining, the second, the third, and the fourth components by reading the questions that have been used to measure each component, So that accordingly, the naming for each component will be, component 1 is about clarity of information. Now it is already named. Component 2, if we read the items of questions in component 2, they are asking about decency and appropriateness. So the name will be given as such. The third component, according to the meanings or the items of questions, it is helpfulness and contact person. That is helpfulness of contact person. The fourth component, reliability of agreements. So the components will be named hereafter as in such a way. So we do have these 4 components finally, based on the 16 items of questions. So if you calculate then after, based on the 16 items of questions which are placed in each component, you can calculate the descriptive statistics for these items of questions in each component, for component 1, for component 2, 3, 4, and finally the total. You can calculate the minimum, the maximum, the mean, and the standard deviation. Because each item of questions are answered based on a scale ranging from 1 up to 7. So they do have a score there. So that you can run descriptive statistics and check which component have the higher minimum and standard deviation and the lowest mean and standard deviation. Highly rated component and lowly rated component could be appreciated by doing this factor analysis. So this is all about factor analysis and principal component analysis, I think the theoretical idea.